Hello everyone, I welcome all of you in this session. So dear children, in previous lecture we have discussed about the topic similar triangles. We will be continuing the same topic in this lecture. But before discussing today's lecture, I would like to recapitulate the main pointers that we have discussed in the previous lecture. So first we discussed in previous lecture is congruent figures. So, two geometrical figures are said to be congruent if they are equal in size and same in shape. For example, if we take two circles of same radii, then the two circles are said to be congruent to each other. And similarly, if we take two ATM cards of a same bank, they are also said to be congruent to each other. And two pages of a same copy are also said to be congruent to each other. Now next one, we have discussed that the similar figures. Two geometrical figures are said to be similar if they have same shape but different sizes. Same if we take the example of two circles of different radii, then the two circles are said to be similar to each other. And two equilateral triangles are also said to be similar to each other. And we have also discussed that we sum up the whole definitions that all congruent figures are similar to each other, but all similar figures need not be congruent to each other. Now today we are going to discuss about the similarity of two triangles. But before discussing the similarity of two triangles, we generalize the result here, the similarity of two polygons. Two polygons having same number of sides are said to be similar. First one, if their corresponding angles are equal and their corresponding sides are proportional. Now in particular, two triangles are said to be similar. So the topic is for the day is similar triangles or similarity of triangles. So two triangles are said to be similar if first condition is their corresponding angles are equal, and the second condition is their corresponding sides are in the same ratio. To understand this concept, let us take an example of two triangles. If we take two triangles like triangle ABC ABC triangle and another triangle PQ and R like this, PQR triangle. So here, if angle A of a triangle A is equivalent to 60 degrees or 50 degree, and angle B is equal to 60 degree, angle C is equivalent to 70 degrees. And in triangle PQR, angle P, the measure of angle P is 50 degrees, angle Q 60 degree, and angle R equals to 70 degrees. And the sides of a triangle ABC are, suppose let it be AB equals to 14 centimeter, BC equals to 10 centimeter, and side AC is equivalent to 12 centimeter. And in triangle PQR, if we take the side PQ is equivalent to 7 centimeter, then side QR equals to 5 centimeter, and the side PR equals to 6 centimeter. So here in triangle ABC, in triangle ABC and triangle PQR, triangle P, Q and R, we have angle A of triangle A, angle A is equivalent to angle P. Why they are equal? Because their measures here equals to 50 degrees. Similarly, angle P here, then angle B is equivalent to angle Q equals to 60 degrees, and angle C is equal to angle or of a triangle PQR angle R is equal to 70 degrees. Also, the ratio of their corresponding sides means the side AB and side PQ. So here also we can write this AB by PQ is equals to side BC upon side QR and further equals to AC side is equal to side PR. So if we look at these corresponding sides of the two triangles, so here AB is equal to 14 centimeter and PQ is equal to 7 centimeter. The ratio between these corresponding sides we observe here, it equals to 2/1. So in these two triangles, their corresponding angles are equal and their corresponding sides are in the same ratio, then the two triangles are said to be similar to each other. We know that triangles are special types of polygons, but the two conditions mentioned in the definition of similar triangles are dependent on each other. It means if one of the condition is fulfilled, then other condition will automatically hold. In other words, we can say that if any of the two conditions is fulfilled, either their corresponding angles are equal and their corresponding sides are proportional, then the two triangles are said to be similar to each other. Also, further look at the two triangles again, ABC and triangle PQR. So three angles of a triangle ABC are respectively equal to the three angles of the other triangle P, Q and R, then the two triangles are said to be equiangular triangles. So a famous Greek mathematician Thales in 600 BC gave us an important truth relating based on these equiangular triangles. He stated that if the ratio of any two corresponding sides of two equiangular triangles are always same irrespective of their sizes. So on the basis of this fact, the theorem based on this fact is known as basic proportionality theorem. First of all, what the basic proportionality theorem is and what is the statement of the basic proportionality theorem. A line drawn parallel to one side of a triangle intersecting the other two sides of a triangle at two distinct points, then the two sides are divided in the same ratio. So this theorem is very important as far as the examination point of view. So let us prove this result, that is known as basic proportionality theorem, or we can say that it is also known as Thales theorem. Basic proportionality theorem. Or we can say it as Thales theorem. Thales theorem. So first of all, understand the statement of the basic proportionality theorem. A line drawn parallel to one side of a triangle. First of all, let us draw a triangle ABC This one is a triangle ABC, A, B and C. The statement is a line is drawn parallel to one side of a triangle. Let the line segment be here DE, and according to the statement of the theorem, this DE is parallel to the one side, that is BC, of a triangle ABC. Then it divides the two different sides, means AB side and AC side, in the same ratio. First of all, what the given is here, given a triangle ABC in which DE is parallel to BC. Then to prove, this parallel line DE divides the two sides AB and AC in the same ratio. That is AD, we have to prove here, AD by DB is equivalent to AE by EC. Let us have some construction here in this triangle. So first of all, if we join this B and E, it is by construction. Join BE, and from the vertex BE, draw a perpendicular on side AB. Let the perpendicular be here EF. This is perpendicular. And also join DC. This is DC line here. We join this, and from this vertex D, we draw another altitude on side AC, and we call the altitude as DG. This one. So now here we can write this construction. First of all, construction. Join EB, or we can say it as BE. Join BE, comma CD, and draw DG perpendicular on AC, DG perpendicular on AC, and EF perpendicular on, this is EF perpendicular on the side AB here. Now let us consider a triangle here ADE. Can anybody here, what is the base of this triangle? If we take this same smaller triangle here A, D and E, which side is the base here? Here we have two bases, because we have two perpendiculars in this triangle A, D and E. If we take the perpendicular EF here, this EF is the perpendicular on AB, or we can say that it is the perpendicular of AD as well. So if we take triangle A, D and E, so what is the area of this triangle A, D and E? So we know that in earlier classes that area of a triangle is equal to 1/2 of base into altitude. So we are going to prove this now. So proof of this theorem, or proof, area of triangle ADE is equal to, yes, what will be the area of triangle AD here? Yes, it is 1/2 of base into altitude. So it is 1/2 of base. Base is here, the side AD, we can write it as AD, and altitude is here, this EF. Similarly, from the same side, if we take triangle ADE, we take the one base here from this side, that is AD segment here. But from the same side, that is AB, we take another triangle, that is this triangle B, D and E. And here this angle is an obtuse angle, and this angle be an acute angle. We know that in an obtuse angled triangle, the altitude always lie outside the triangle. So BDE is an obtuse angled triangle, and its base is BD, and its altitude is always in its exterior. From this vertex E, draw a perpendicular from E to, we get EF here perpendicular. For this triangle, obtuse angle triangle, BDE base is BD and altitude is EF. Similarly, area of a triangle BDE is equal to 1/2 of base for this obtuse angle triangle BDE. Base is BD into height is same EF. Now look at the to prove condition here. What we have to prove? Side AD by DB. Now we have area of triangle ADE is equal to 1/2 of this segment AD is here into EF, and similarly in the triangle area of triangle BDE it is 1/2 of same side BD, here it is BD into EF. So here in to prove condition we have AD divided by DB, so we put them in the division form, it is AD divided by DB. So we divide the above two, therefore we can write area of, so AR means here area of triangle ADE divided by area of a triangle this BDE is equal to, when we look on these right hand sides of the above two mentioned equation here, we have 1/2. If we divide these right hand sides, 1/2 and 1/2 will cancel out, and EF will be same here, they will also cancel out here, and we can write here it is AD divided by BD, and we call this one as first equation. So if we take two triangles from the side AB here, first triangle is ADE and the other triangle is BDE, we get the ratio of their areas of these two triangles is equal to the side AD upon BD. Similarly, we can prove from this side, similarly from this side area of a triangle we can say it as area of AED or ADE. So area of ADE divided by area of CD and E. Area of CDE is equivalent to, same in these two triangles we have AD by DB, but from these two triangles AED or ADE and CDE we get it is AE divided by EC. AE upon CE, or we can write it as EC and call this one as equation 2. Now look once again at the to prove condition here, it is AD divided by DB, AD divided by DB is equal to AE divided by EC. When we observe the two equations here, the right hand side of the first equation is AD divided by DB, yes, and the right hand side of the second equation is AE divided by EC. But look at the left hand sides of these two equations. Here we have area of ADE and we have area of AD, same in left hand sides here. Now look at the denominators here, area of BDE and area of CDE. These two denominators are not same here, but look at the figure here where these two triangles lie. So area of BDE, so triangle BDE here and a triangle CDE, this triangle CDE. Clearly these two triangles lie on the same base, that is DE, and between the two parallels DE and BC. You have already learned this result in class 9, that when two triangles are on the same base and between the same parallels, then the two triangles are always equal in area. So same result we use here, since triangle BDE and triangle CDE or lie on the same base, Yes, what is the same base here? DE, exactly. So a triangle BDE and triangle CDE are lie on the same base, that is DE, and between the two parallels or same parallels. Between the same parallels. Therefore, we can write here area of triangle BDE. This area of a triangle BDE is equal to area of a triangle CDE. C, D and E, and we call this as third equation. Now we compare equation 1, we compare equation 2, and we compare equation 3. When we compare all the three equations, we get here area of ADE divided by area of BDE. But in equation 3rd, area of BDE is equal to area of CDE. In equation 2nd, we have area of CDE. So on comparing all the three equations, we get AD divided by BD is equal to AE divided by EC. So from first, second, and third, we get AD divided by BD is equal to AE divided by EC. This is the theorem all about when we have a triangle and we have one line parallel to one opposite side, then it intersects the two sides at two distinct points here D and E. Then this line divides the two sides AB and a side AC in the same ratio, that is AD divided by BD is equal to AE divided by CE. Now on the basis of this basic proportionality theorem, we have a corollary, that is deduction from this theorem, basic proportionality theorem. So the corollary is if in a triangle ABC DE is parallel to BC, then AB, or we can say that AD by AB is equivalent to AE by AC. So first of all, this is the corollary based on this basic proportionality theorem. If we have a triangle ABC and a one line DE is parallel to one side BC, then we have to show AD by AB is equal to AE by AC. So let us draw a triangle ABC here, ABC, in which DE is parallel to the side BC of a triangle. So proof of this corollary is in triangle ABC DE is parallel to the side BC. DE is parallel to the side BC. Therefore, AD, we can write it as AD by DB is equivalent to AE by EC. AE by EC. The reason is by basic proportionality theorem. By basic proportionality theorem. Or we can write it as, if we take the reciprocal of the two, we get DB by AD is equivalent to here EC upon AE. The reason is by reciprocal property. By reciprocal property. Now look at the, to prove condition here, we have to prove AD upon complete line segment here AB but we have DB and AD. But if we have DB and if we add DB to AB, then we get the complete line segment here AB. So for this we can write it as AD or DB by AD if we add 1 to left hand side and same one to the right hand side here, equals to EC upon AC plus 1. Now taking here, so it is AC divided by here it is AE, this is AE here. Then if we cross multiple here the two, we get it is DB, we simplify this, plus 1 into AD is AD whole divided by AD. Then here same EC plus 1 into AE is equal to AE whole divided by AE. Now we have two line segments here, DB plus AD. Look at the figure, DB plus AD, we can write DB plus AD equals to AB here. So here we can write, it implies from this DB plus AD is equivalent to AB divided by this AD, then is equivalent to here, this is EC plus AE. EC plus AE, we can write it equals to AC divided by AE. Or again if we take the reciprocal on both the sides, we can write AD by AB is equivalent to AE upon AC. This is the corollary that we use the basic proportionality theorem here to find the side AD upon complete side AB is equal to the line segment AE upon the complete side of the triangle ABC here AC. So this is the proof of this corollary, that when we have a triangle ABC and a line is parallel to the one side of the triangle, then we can say that this line divides the two sides here in the ratio AD upon AB is equal to AE by AC. So this is all for today's lesson. We'll meet you in the next session. Till then, take care of yourself.